Welcome you all. Today we are going to discuss about the multicollinearity problem of the regression model. Multicollinearity, one of the important assumption of classical linear regression model was that no multicollinearity among explanatory variables. That is important. It is important that no multicollinearity among the independent variable. No relationship between the independent variable is termed as multicollinearity. That is one of the important assumption of classical linear regression model is that there is no multicollinearity among the explanatory variable, that is among the independent variable. That is the relationship between independent variables are termed as multicollinearity, and this term is due to the Ragnar-Frisch, and according to him, the existence of a perfect or exact linear relationship among some or all explanatory variables of a regression model is termed as multicollinearity. That is, the existence of a perfect or exact linear relationship among some or all explanatory variables of a model is termed as the multicollinearity. That is, the existence of a perfect or exact linear relationship among explanatory variable is termed as the, here the term linear is also important. According to Ragnar-Frisch, he meant the linear relationship among the explanatory variable. And the difference between perfect or exact and inexact or the imperfect relationship can be explained as follows. The distinction between perfect and not perfect relationship can be explained as follows. In this model, suppose that we have a regression model of k independent variables involving x1, x2 to xk. And the perfect relationship among these variables or among these independent variables can be written as lambda 1 x1 plus lambda 2 x2 plus lambda k xk equal to 0. That is, the relationship, their sum will be equal to 0. There exists some perfect relationship between these variables. This is the meaning of perfect relationship. If the relationship is not perfect, nowadays we use this term multicollinearity to denote not perfect models also. That is, this includes not only the perfect model, that is multicollinearity problem exists in the case of the not perfect model also. In the case of the not perfect model, or the not perfect model can be specified as follows. That is lambda 1 x1 plus lambda 2 x2 plus lambda k xk plus vt. Here this vt is the stochastic terms or the error term. It depends upon some other variable or it is influenced by some other variables also. Suppose lambda 2, we suppose that lambda 2 not equal to 0. Then the equation 1 can be specified as x2 lambda 2 equal to, if lambda 2 not equal to 0, then x2i equal to lambda 1 x1 divided by lambda 2, then lambda 3 by this minus then x2i equal to lambda 1 by lambda 2 into x1i, or lambda 1 x1i by lambda 2 minus lambda 3 by lambda 3 x3i by lambda 2 to lambda k xki by lambda 2. This is the x2 in the case of the first equation if lambda 2 not equal to 0. And in the case of the second equation, similarly, if we assume that lambda 2 not equal to 0, then x2i can be specified as the same way, lambda 1 x1i by x2, lambda 2 minus lambda 2 x2, lambda 3 x3i by lambda 2 to lambda k xki by lambda 2 minus 1 by or Vt by lambda 2. That means it is influenced by some other factor also. This is the meaning of the perfect, and that is, here the x2 is influenced not only by the independent variable, it is also influenced by some other factors. It is the meaning. This is the meaning of the not perfect, and this is the meaning of the perfect relationship. And this multicollinearity can be explained as follows. Here we have three variables. The first variable is first listed variable x2 is given as 10, 15, 18, 24 and 30. Here x3 is defined as 50, 75, 90, 120 and 150. This means the x through x, this means that x3 is 5 times than, or 5x2 is the x3. That is 5 into 10 equal to 15, 5 into 15 equal to 75. That is x3 equal to 5x2. That means there exists some linear relationship. And x3 is constructed as follows. That is here x 52, 75, then 97. Here we have added some constant variables, that is 2, 5, 7, 9, etc., 9, 12, etc. That means here also there exists some relationship. This relationship, this multicollinearity can be visible from if we examine the correlation coefficient. Also, the correlation coefficient in the case of this x2 and x3 will be sometimes 0.99. That is, by examining the correlation coefficient also we can see with the whether there exists multicollinearity among the variable. This is an example for the multicollinearity. Here the multicollinearity is explained in the form of the Ballantyne's view, that is in a diagrammatic form. In the case of the first diagram, there exists no relationship among the variable, that is there is no collinearity. Here we can see some collinearity. Here this the collinearity increases, moderate, high, and very high collinearity in this equation. This is the meaning, or there are some overlaps among the variables. This overlap is termed as the multicollinearity. We have seen into equations earlier that equations are linear, but in some cases we can see the variables will be non-linear also. There will be non-linear relationship also exist among the model, but here there exists some relationship between this independent variable, that is x1, its square is x1 bit, x1 square is the second variable, second independent, and this cube term is the, or cubic form of the x1 is the third variable. In this case also, in this case the relationship is non-linear, and therefore the model like this do not violate the assumption of no collinearity. That is, here the relationship is non-linear and therefore it do not violate the assumption of no multicollinearity. But if we examine the correlation coefficient, it will be very high, and it will make it difficult to estimate the parameters with greater precision, or in this case the standard error will be small. These are some of the problems associated with these types of estimation. That is, what is the meaning of this, or why the classical linear regression model assumes no multicollinearity? The reasons are given as follows. First one, if multicollinearity is perfect, as we have seen in the first equation, the regression coefficient of the x variables are indeterminate. That is, in the case of the perfect, if the relationship is perfect as given in this one, then the regression coefficient will be indeterminate, that is lambda 1, lambda 2, lambda 3, or beta 1, beta, whatever the notations we use will be indeterminate, and the standard errors will be infinite. We will get an indeterminate coefficient for the x variable or independent variable, and their standard errors will be infinite. This is one of the important reasons why the classical regression model assumed no multicollinearity. But of the reason, in the case of the perfect multicollinearity, or in the case of perfect multicollinearity, if multicollinearity is perfect, the regression coefficient of the independent variable will be indeterminate, or they are indeterminate, and their standard errors are infinite. Second one, if multicollinearity is less than perfect, as we have seen here, it is less than perfect or it is not perfect, then in that case the regression coefficient will be determinate, but it possesses large standard error. That is, this will be the coefficient, or the significance will be questioned. Here in this case, the regression coefficient will be indeterminate, as well as their standard errors will be infinite. These are the two consequences consequences of perfect multicollinearity. If multicollinearity is less than perfect, the regression model assumes the regression coefficient. If the regression model is less than perfect, then the regression coefficient will be determinate. The regression coefficients are determinate, but the standard will be very high. These are the two consequences of multicollinearity, and therefore the classical model assumed that no multicollinearity among the regressors or among the independent variables, and that means the coefficients cannot be estimated with greater precision or accuracy. We cannot estimate the coefficients with greater precision, or we cannot estimate the coefficients with greater precision or accuracy. Why this? Or there are several sources of multicollinearity. According to Montgomery and Peck, the multicollinearity may be due to the following factors. First, the data collection method employed. The data collection method employed, for example, sampling over a limited range of values will give the multicollinearity. That is, if the sample size is very small or over a limited range, then there will be the possibility of multicollinearity. Second important source is the constraints on the model or in the population being somebody. If we impose some constraints on the model, then also there are every chances for the multicollinearity. Then the third problem is the model misspecification. If model is not correctly specified, then also there will be the problem of multicollinearity. And in the case of an over determined model also, in the case of an over-determined model also, or if the model is over-determined, then also there will be the chances for the multicollinearity. What is the meaning of this over-determined model? When the model has more explanatory variables than the number of observation, then it is termed as over-determined. That is, the number of explanatory variables will be more than the number of the observations. In that case, also there are every chances for the multicollinearity. So therefore, the important sources of multicollinearity are the data collection method employed, the constraints we impose on the model and the population being sampled. Third one is if the model is not correctly specified, and fourth one, in the case of over-determined model. Our determined model means the number of explanatory variables will be more than the number of observations. Say if the number of independent variable is 7 and the number of observation is only 5, that type of models are known as over-determined model. These are some of the important sources of multicollinearity.